Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asghar, and today we will learn how to build multiplication table. This is actually under the subject of symmetry and magnetochemistry. So far in our first lecture we have discussed quite important information to build multiplication table for different molecules. For example, we were studying the ammonia molecule, and we have successfully evaluate the and describe the symmetry elements and symmetry operations that is found in NH3 molecule. Moreover, we have discussed some of the important rules that would be helpful for to build the complete symmetry table, as well as symmetry table, multiplication table and symmetry table of any molecule. We have discussed these rules in quite extensive way, and last time we have studied about the symmetry operations, and most of important was the improper rotations. We have discussed that what happened if we applied C3 rotation to a molecule, and what happened if we applied C3 twice to ammonia molecule. And I have already told you that you people should have to write the reactant and the product. This is actually the kind of reactant, is a kind of identity, and we should need to write the product after performing that particular symmetry element or symmetry operation. That this would be quite helpful for us to maintain, to establish, to build a character table and multiplication table of any molecule. So this time we are going to analyze complete set of symmetry operations, and we are going to analyze the products after performing different operations and elements on the NH3 molecule, and subsequently I will tell you how to build a correct multiplication table of this molecule. So now we will talk about the sigma v1, sigma v2 and sigma v3. We have discussed the identity C3 and C3 twice already. This time sigma v1. So if I talk about the sigma v1, it means that we are taking hydrogen A, and this is actually the axis or plane of symmetry to that molecule. Sigma v1, 1 for the A, 2 for the B and 3 for the C. So it would be quite clear in your mind that if I talk about the sigma v1, then the cutting angle or the mirror image angle of this molecule would pass through the HA molecule. And similarly, if I talk about the sigma v2, then the HB would be considered the mirror plane axis, and this for sigma v3, HC would be considered for mirror plane of this molecule. So what happened if we applied sigma v3 to this molecule? If the plane of symmetry is of this angle, then after applying sigma v3, then we should have to bear in mind that HC, which is hydrogen C, should not be changed its position, because this is actually the plane of symmetry for sigma v3 axis. So what happened if we applied sigma v3 and it passed through the hydrogen C molecule atom? Then we can clearly see that actually this is only the shifting of HA and HB to each other. So HB will shift its position to the HA, and HA subsequently join the place of HB. So that would be the product after applying sigma v3 to NH3 molecule. And this is also for the sigma v1. This rule is also applicable for sigma v1 and v2. What happened if we applied sigma v1 to this molecule? We will definitely the plane of symmetry or plane of mirror should be from HA and nitrogen, while there should be no change in HA. Here we can see there is no change of position of HA, but actually the shifting of position of HC and HB, because the mirror image become over HC become join over here, and subsequently HB will definitely join HC position. So this will be the sigma V1 of after applying sigma V1 to NH3 molecule. So in the case of sigma V2, I have already told you sigma V2 means the plane mirror should be from HB atom. So this is the result after applying sigma V1, V2 and V3 and C3 and C3 twice. So it would be easy for us to now construct a multiplication table of NH3. So before construction of multiplication table for NH3 molecule, we should have to write the complete set of symmetry operations in a row and in a column. So in a row we can set E, C3, C3 twice, sigma V1, sigma V2, sigma V3, and subsequently as E, C3, C3 twice, sigma V1, sigma V2 and sigma V3. So we have written all the possible symmetry operation in a row and as well as in the column. Now we should have to commute the symmetry operations from the row to the column. So it means that we should have to commute this identity with this identity, then this identity with this C3, the identity then with C3 twice, identity then with sigma V1, identity should commute with the sigma V2, and identity again commute with the sigma V3, and we should have to write the results of their commutation and their after their product. So after completing this row of extensive operation, we should go to the another operation which is C3. After applying this C3 to identity, we should have to write the symmetry operation result, because this is the operation and this is the operation. If we commute though both operation are symmetry elements, there should be an other operation, and this another operation should be from the same symmetry operations that we have written already for that particular molecule. So we can get a complete array of symmetry operations and elements in a quite comprehensive way. So let's start from the identity first. What happened if we apply identity again with identity? Yes, there will be identity again. So here we can write E again. So what happened if we apply commute identity first to the molecule and then C3? Then definitely this operation would be equal to C3, because we have applied C3 only, identity have nothing to do with the molecule. So it means what happened if any operation commute with identity, the resultant would be the same of that particular operation that commuted with the identity. So same is the case with C3 twice. What happened if we applied identity to the molecule and then C3 twice to the molecule? The resultant would be C3 twice. So here is the complete description of the first operation that would occur between the first column and the row. It means that identity commute with the identity and yield the identity operation, then identity with C3 rotation operation and identity with C3 twice, it also yield C3 twice. Same when identity performed and then we performed sigma V1, the result should be sigma V1 and sigma V2 and sigma V3 subsequently. So let's talk about a more complicated one. Herein we must apply C3 to the molecule, then we need to apply identity. Yes, what happened? If we apply C3 to the molecule, then identity to the molecule, there is C3 again, because identity is actually doing nothing to that molecule. So the operation, the resultant operation is C3 for this one. The next one, the C3 should commute with the C3. What happened? If we applied 2 times C3, what happened? I already told you that if we apply C3 2 times, here I have written that if we applied C3 2 times, then it means this is actually the if we applied C3 2 times, then it will be equal to C3 twice. So if I applied C3 and then again C3, that the result should be the C3 twice. For example, you can take this HB as a reference. So I am going to apply C3 to this molecule in counterclockwise or anti-clockwise rotation axis. So what happened if I applied just C3? This B will definitely go over there, and here we can see that HB is here, and HC subsequently will join the place of HA, and HA will join the place of HB. So this is actually the result after C3 operation. Now I would like to apply again C3 to this molecule in anti-clockwise fashion. What will happen? This B will replace the place of HC. Here we can see that, and this is actually the resultant after applying another C3 after applying C3 to this molecule. So it means that if we apply C3 and C3 operation, the resultant would be the C3 twice, and we should have to write the C3 twice here. Now let's talk about the C3 and C3 twice. What happened if we apply C3 first and then C3 twice? That would be equal to identity. How? If this is the identity of our molecule, what happened? The B after applying C3 is over there. Now after applying again C3, the B is here, and we need to apply C3 third time. The B will definitely join the place of C, and we will get that again the identity. This is actually the starting of the molecule, which is equal to the identity. So it means that if we apply C3 operation first to the molecule, then C3 twice, it would be equal to identity. Here we can see that this is equal to identity. And what happened if we applied C3 rotation then sigma V? What will happen? So first of all, we need to apply C3 rotation. C3 we have applied, we will get like this. And what happened if the sigma V1 is applied to this molecule? Sigma V1 means we should have to take this angle as a plane of symmetry. It means we should pass the plane of symmetry from hydrogen A and nitrogen. So what will happen? The B will go to the place of C, and C will go to the place of B. This is actually the sigma V2. This is actually the sigma V2. If we can say this is, yes, I would like, this is already I told you that this operation would be equal to sigma V2. So herein we can write the sigma V2 after applying C3 and sigma V1. So what happened if we apply C3 and sigma V2? You need to think about this. C3 and sigma V2 means from the B. So from the B plane of axis, if we apply sigma V2, then the position of HA and HC will change. They will change their position with each other, and we will get the product resultant, which is equal to the sigma V3. So which is equal to the sigma V3. Here we can see this, which is equal to sigma V3. So what happened if C3 is commuted with sigma V3. So first we need to provide the C3 rotation, and we will get like this molecule, and then we need to apply the sigma V3. Sigma V3 is actually from the C molecule, C hydrogen. It passes from the hydrogen C and nitrogen. The mirror image of sigma 3 is actually this from this axis, and the positions of HA and HB will change with each other, and this result would be equal to sigma V1. Here we can say this is the actually sigma V1. So we can write here sigma V1 as a symmetry operation and symmetry product of this after this operation. This can be done with the other symmetry elements and operation of the ammonia molecule. So far we have completed the two symmetry elements and operation from the column, and we have commuted all the symmetry operations in the rows with these symmetry operations. Now let's talk about the third one, which is the C3 twice, and we have already discussed the C3 twice, and let's talk about the sigma V1. We should have to commute sigma V1 with the other symmetry operations in the rows. So first of all we need to apply sigma V1 with the other symmetry elements. So if we apply sigma V1 to a molecule, then it should be the same operation, because any operation that is commuted with the identity, it yields the similar operation that is commuting with the identity. So it means that here we can write sigma V1. So after applying next step, if after applying sigma V1, we should have to commute sigma V1 with the C3. So what will happen if we apply sigma V1 with the C3? So first we need to apply sigma V1. Here we can say this is actually sigma V1, and this is the axis plane of symmetry for the sigma V1, and we know that HA and N will be the constant, and the plane of symmetry is actually from this angle HA and N, but the position of B and C would definitely change. So C occupy the position of B, and subsequently B will occupy the position of C. So this is the sigma V1. We need to apply sigma V1 first to the molecule, and we will get the product like this. Now we should have to apply the C3 to this molecule, so to this product. So we need to apply C3 anti-clockwise. What will happen if we applied C3? This HB, we should have to look at the HB. So this HB will definitely replace the HA and occupy the place of HA, and HA will join the place of HC, and subsequently HC will definitely will join the place of HB. So the structure of this molecule would be like this, the product would be like this, and this operation is obtained after applying sigma V3. So we can set this after applying sigma V1 and C3, the resultant should be sigma V1. We can set this is sigma V3. We can set this is actually the sigma V3 after applying sigma V1 and C3. Their resultant should be sigma V3. So what happened if we applied sigma V1 and C3 twice? The resultant should be sigma V2. How we can get sigma V2? Actually, after applying sigma V1 and C3 twice, we will get the sigma V2. So after what would be the result after applying sigma V1 and then again sigma V1? If we applying sigma V1 two times, then the resultant would be the identity. There is no change in the molecule, so we should have to write the identity after applying sigma V1 with the sigma V1. Now let's talk about the sigma V1 operation with sigma V2. We will get what kind of symmetry operation after applying sigma V1 and sigma V2. Yes, we need to write sigma V1 first and then sigma V2. Sigma V2 means there should be a B. Its angle of axis plane of symmetry should be from B. So the B should be same, and but the position of A and C is different. So this will happen only when we will apply the C3 twice to this molecule. So we should have to write like this one, C3 twice. Again, what happened if we apply sigma V1 and sigma V3? We will get the C3 rotation. So after getting this all, we need to apply the fifth symmetry operation of this ammonia molecule that is written in the column with the different symmetry operations in the row. So one by one we should have to multiply all of them. Sigma V2 E1 E. So the resultant should be sigma V2. Sigma V2 commute with C3. What will happen? We need to apply sigma V2 first, then C3. The resultant would be the sigma V1. What happened when sigma V2 is actually applied to the C3 twice? The resultant is sigma V3. So this is actually the commutation result after applying sigma V2 with sigma C3 twice. What will happen when sigma V2 is actually commute with sigma V1? V2, we need to apply sigma V2 first and then sigma V1. The resultant is equal to C3 axis of rotation. It would yield a similar operation that is obtained after performing C3 to the identity. So sigma V2 and sigma V1 will yield the C3 operation. Sigma V2, then we need to commute the sigma V2 with sigma V2. What will happen if we apply sigma V2 two times? It will definitely yield the identity, and we have already discussed in detail. So what happened when sigma V2 commute with sigma V3? It will yield the symmetry operation which is equivalent to C3 twice. So this is actually the C3 twice we have written. I have already told you the symmetry operations that is obtained after the commutation of this column symmetry operation with the row symmetry operation. So the last one is actually sigma V3. Last one is sigma V3. Now we should have to multiply or commute the sigma V3, which is the last operation in this column, and we should have to commute this sigma V3 with all the symmetry operations present in the row. So first of all, sigma V3, when we commute sigma V3 with identity, the resultant would be sigma V3, because sigma V3, whenever any operation commute with the identity, the resultant would be the same as that of operation commuted with the identity. So in the next step, what happened when we applied sigma V3 to the molecule and then C3 to that molecule? The resultant would equal to sigma V2. Yes, we have to learn this by using the simple diagrams. We need to learn by trying the products after applying the specific symmetry elements and operations. It would be quite helpful to evaluate. It would be quite helpful to construct the correct multiplication table of any molecule. So what happened if we applied sigma v3 to C3 twice? This would be equal to sigma v1 operation, and sigma v3 with sigma v1 would equal to C3 twice, and sigma v3 operation and then sigma v1 operation would yield the operation which is equivalent to C3 twice. So what happened when we applied sigma v3 to sigma v2? It would definitely yield C3 rotation. And what happened if we applied sigma v3 with sigma v3? So actually this is the square sigma v3 square, and it will definitely yield the identity of the molecule. So here is the complete multiplication table for the symmetry operations in NH3. I do believe that you will get the point, and you are now able to construct the multiplication table for the NH3 molecule. This is all for this lecture. Thank you very much.